Good evening, everyone. My name is Jyoti Sharma, and this is week 4. The session will be from 6 to 8. So let's start. First, I want you to remind that what we already have done. So in week 1, we started with the introduction about the environment, what different compartment we have, and how the source will give from the source we will have some pollutant A. That pollutant A will go to the environment, and to the environment it will go to the receptor, and receptor here is nothing but the human being. So this we learned in week 1, along with what different parameter we can use um, to get to know the quality of water and air. And in air we particularly focused on the particulate matter here. So this we covered in week 1, and in week 2 we started with the partitioning coefficient. Actually, it is very important because, as I told you, whenever there will be the process, and that process will give you pollutant A, and that pollutant A will can go to the water, can go to the air, can go to the soil. So it depend on its affinity and its attachment to that particular molecule, either that molecule of the air or water or the soil. So based on that, we so this was very important for us to know about this partitioning coefficient, and we learned how one pollutant A can move from soil to water, water to soil, air to water, water to air. So such kind of things we try to cover. This was in week 2nd. In week 3rd, we started with the introduction to environment monitoring and sampling. We talked about the calibration, we talked about the accuracy, we talked about the precision, and that's how, because this subject is all about quality monitoring and analysis. So it's very important, whatever monitoring we are doing, we should have some confidence in that, because based on that only some policies are formulated. So that's how we started this environmental monitoring and sampling from week 3, and now we will continue it in week 4. And again, I encourage you people to please participate, please give the answer whatever it is wrong or right, because I am here to correct you. I'm here to make you understand why that option is incorrect or this option is correct one. So please do participate. And yeah, so in this week 4 we will start with environmental analysis of organics in water. So if we do have any organic compound, most of the organic compound are non-polar in nature, and if we have such kind of compound in water, then how we can do the analysis of that, how we can get to know the concentration of that. And it is very important to understand what is the chemical property of that organic compound, or you can say the pollutant A, because whatever instrument you are using, that instrument, the use of that instrument will be dependent on the chemical property of your um, pollutant A. So that's how, whenever we are doing any kind of monitoring, so it's important to know its affinity, its partitioning coefficient, its concentration, its physical and the chemical property, because based on that only we will select what instrument we will use to monitor it, right? So likewise, we have a lot of MCQ question based on this topic, and yeah, so this is how we're gonna proceed with it. So we are starting with GC, and this GC is nothing but gas chromatography. So why is extraction often required before GC analysis of water sample? So I have 4 options here. GC cannot detect organic compound. GC require analytes to be in gaseous or volatile form. Water improve the GC separation. Extraction increase pH, so to maintain the pH. So what do you think? What should be the right answer for this? Why we do need the extraction? Any guess about this? Okay, so here the answer will be B, and let me tell you why. Okay, first see the options that we have right now. The first option is gas chromatography cannot detect organic compound. No, this is the wrong statement because GC is mostly used to detect the organic compound. So this is the wrong statement that I put here. So A is not the right answer. The second is GC requires analytes to be in gaseous or volatile form. This is right. Whatever we have pollutant A, let's say we have pollutant A, pollutant B, pollutant C, and we have these are in, let's say, water, and these are firstly these will be organic if we are monitoring it using or analyzing it using GC. So this A, B, and C. The principle of gas chromatography is like this: these A, B, C will move, and then based on their movement we will detect the signal in the machinery. So to make it moved, right, to make it moving, the analytes should be in gaseous or volatile form only, right? So this is the right answer. Then water improve the GC suppression? No, actually we need the extraction because we can't use any pollutant A in water whenever we are doing the analysis in GC. Water will not help us to separate um, different pollutant, right? So that's how this is again the wrong statement. Extraction increase pH, so to maintain the pH? No, pH and extraction is two different things. This option is not relevant here. So B answer is the right one. And I think okay, yeah, I have few slides to show you the principle of gas chromatography and why the B option is the right one. So for example, if you have any liquid sample, if you have liquid sample, so first what you have to do is and here you have sample injection unit, so heat and vaporize each component. So what we are doing is uh, our analytes, so let's say our analytes is A, right? A should be volatile enough so that it can go uh, from water to it can move along with the carrier gas, right? And that's why B answer is the right one. So what will happen if we have analytes A? Let's say if it is a, then this A will move along with the carrier gas, and based on its affinity of this A with the carrier gas, it will depend how it will move, to what distance it will move. It may be that this A will move up to this distance, it may be up to this one, or so there may be some cases that um, so for example, we have analytes A, B, and C. So it may be that because of its affinity, based on its partitioning, A may reach at the first position, B will reach to the second position, and C will reach to, let's say, to the third position. But they will reach to the detector, right? And based on the electrical signal, it will decide how much we have of that particular compound. So this is how we can exploit the gas chromatography. But the thing is that this gas chromatography is mostly for the organic compound, the first thing. The second thing is, for the gas chromatography, your analytes should be either in the gaseous phase or in the volatile form. This is the requirement, otherwise we can't use such kind of instrument. These are very sophisticated instruments. So so that's why B answer was the right one. And yeah, I think this text will help you to understand more about gas chromatography. So this is nothing but it run on the principle of partitioning, and we already have covered this partitioning in the week 2 uh, of volatile sample with the gaseous mobile phase and liquid stationary phase. So what we have is, we have liquid stationary phase and gaseous mobile phase, and based on its affinity of this volatile sample, either its affinity is more with that liquid stationary phase or not, based on that affinity or based on that partitioning, molecule will go at the first position, at the second position, and based on that we can detect what chemical component it can be, right? So this is how this gas chromatography work. So I just read it so that you have very clear idea about gas chromatography. So the principle of separation in gas chromatography is partition. Very clear. The mixture of component to be separated is converted to vapor and mixed with gaseous mobile phase. The component which is more soluble, this is actually very important. So the component which is more soluble in stationary will travel slower, and that's how it will reach to the detector at the later stage, right? The component which is less soluble, which do not have solubility in the stationary phase, will travel very fast and will elute out first, and that's how the signal, this will give us first signal. So no two component have same partition coefficient. We already have learned about this partition coefficient. So the component are separated according to their partition coefficient. Partition coefficient is the ratio of solubility of a substance distributed between two immiscible liquid at a constant temperature. I think this is now clear, because we already have learned about this partitioning coefficient, right? So this is the principle of gas chromatography. Okay. So the next question is, which factor primarily determine the choice of analytical instrument? For example, GC or HPLC. And here I have four options: turbidity of the sample, volume of the water sample, chemical property of analyte, and pH of the sample. So I think I received some answer. Yeah. So Lakshmi gave me answer C, and yeah, I agree with this. Because again, uh, if we are talking about these four options, turbidity of the sample, uh, we can remove that turbidity, right? We can remove that turbidity and we can use that instrument. So turbidity is not that big factor for us. We can filter out it, right? Volume of the water sample, water of the volume sample is very important, but we can make manipulation, we can increase or decrease the volume, right? So this is not the primary factor. We can easily manipulate it. Chemical property we can't manipulate, and based on the chemical property we will use the analytical instrument. So as I gave you the example, if we have gas chromatography, then that we can use only when we are analyzing the organic substance, and the organic substance should be either in gaseous phase or in volatile phase. Then only we can use this gas chromatography. So that's why, and we can't change the chemical property. Whatever it is, it will be the same, right? pH of the sample, this will like we can change the pH of the sample also, right? And most of the time instruments are a little insensitive to the pH of the sample. So yeah, C answer is the right one. Okay, so the next question is in gas chromatography using a non-polar stationary phase. So right now the stationary phase here is non-polar. Which compound will elute first? And I have four options here. Naphthalene that have high boiling and is non-polar, hexane low boiling and non-polar, phenol polar hydrogen bonding, benzoic acid polar high boiling. In the gas chromatography, here the condition is that we are using non-polar stationary phase. So which compound will first go to the detector and which substance will go later to the detector? And whether it will go at first or it will go at last to the detector depend on the partition coefficient, right? And partition coefficient is depend on the chemical and physical property. uh okay, I got response again from Lakshmi, that is B, I think. Yeah, you are right. And why the B is the answer? From starting only we are talking that it should be our analyte or pollutant A should be volatile in nature, and to be volatile in nature the boiling point should be low. At a low temperature it should start boiling, right? The temperature, the boiling point of let's say water is 100 degrees Celsius, but what if the compound have just boiling point of 40 degree, and this 40 degree we can achieve in the summertime very easily. So if the compound boiling point is let's say 40 or 50 degrees Celsius, then it can easily change into the volatile thing, right? And if it will be the volatile, then yeah, gas chromatography is the best thing that we can use to analyze that organic compound, right? And that's why this uh, low boiling point is very important for us. If we are talking about this polar and non-polar, because here we are using non-polar stationary phase, so uh, because it is non-polar, then polarity, the effect of polarity is very negligible. Here the effect of boiling point is very important in the case of non-polar stationary phase. So that's how B answer is the right one. And I think I have few things, yeah. So just see about the polarity, because we have four options here, right? Hexane, naphthalene, phenol and benzoic acid. And we know that hexane and naphthalene, these are benzene structure, or naphthalene have the benzene structure, hexane not benzene, but yeah, it is closed structure, but these are very organic in form and these are non-polar. But just see the boiling point is very low for the hexane, that is 69.69 degrees Celsius. And that's why uh, it will go fast with the carrier gas, right? It will go fast to the carrier gas, and that's how the retention time will be very short for this, and this will go fast to the detector. And that's how we can measure it, because each compound have a different signature, uh, at what time it will reach, and what will be the signature. So based on that signature, based on that electrical signal, we can identify, okay, that will be the hexane, and what is that concentration of hexane we have. um, Naphthalene have high boiling point, that is 218. Phenol and benzoic also have a high boiling point as comparison to the hexane, and that's why hexane will go first to the detector. Yeah. Okay, because we are talking about monitoring, we are talking about the instrument, then I think the sensitivity of the analytical method is the one thing that we need to understand very clearly. So this question is based on that only. So the sensitivity of an analytical method is best described as, and I have four options here: ability to measure large concentration, minimum detection limit, number of calibration point, time required for analysis. What do you think? What is the right answer for that? So yeah, so whenever we are talking about the sensitivity, then we are talking about the minimum detection limit only, and that's how B answer is the right one. And let me show you. So this is some graph, that calibration curve that we plot every time. And in calibration curve, what we have in the y-axis, we have instrument response, and on the x-axis we have amount of the substance that we are analyzing, right? So most of the time the instrument will give such kind of graph, or if if sometime I get the accurate, so this will be something like this. Let me clear this. So something like this. So just see this part and this part. So this is something that your instrument is giving the same value, instrument is giving the same response here and here, even if the amount is increasing. Here the amount is increasing, but still it is giving the same response. So that's how it is very important us to know about that minimum detection limit. So for example, if we have any weighing machine, and weighing machine is uh, it can measure from 0.01, let's say, gram. But if we have something in a very minute amount, so let's say we have amount that is 0.001 gram, the instrument response will be just similar to 0.01 gram only. It will not show you that yeah, this is 0.001, but it will show that this is 0.001 gram only. So this is something that we need to know. So whenever sometime if we are talking about the heavy metals, or benzene, or let's say nickel or arsenic, in the atmosphere it is in very less amount, very less amount. So if we gonna measure that, so it is better us to know the minimum detection limit of the instrument. So it may be that we have very low concentration, and our instrument, the minimum detection limit is more than what our concentration we have. So that's how this will be uh, uh, yeah, this will be uh, overestimating. Why overestimating? Because let's say I have nickel in the atmosphere, that is 0.001 gram. Let's say if it is a gram, or you can say milligram per liter. Here it is the concentration we are talking about. So if it is, let's say, 0.001 gram, and because our machine can only measure the weight that is more than 0.01 gram. So even if we are showing that this is very minimum amount that we have in the atmosphere, but it will still give you the value that is 0.01 gram. That's how this is overestimating. This is showing us the value larger than what we have, and our value is very smaller. But because instrument capacity is not to measure that minimum detection, or to measure that smallest amount that we have, so that's how this is overestimating, right? And this is giving us the, like, not reliable result. And for any policy making, it's very important whatever we are doing, whatever we are analyzing, whatever we are monitoring, the result should have some confidence. And that's how this minimum detection factor or limit is very important for us to know. And that's all. Yeah, I think this is the explanation that I have. Anyway, so because it is again very important for us to go little more about the numerical thing, right? So I have a few questions mm, about the equations and about the solving. My MCQs will be MCQ will require you to have a pen and paper. If you have, then I think that will be the better case, because some question are numerical in the form, and I would request you to solve it if you have pen and paper near to you. Okay, so the next question is, if the measured concentration of A is 0.5 mg per liter and method detection limit is 1 mg per liter, then this gives not reliable reading. The compound is definitely absent. The instrument is highly accurate. The extraction step failed. Uh, no. Having the low detection limit is not that the instrument is inaccurate. That is the limitation of the instrument, right? Are you understanding what I want to say? Okay. Here the answer will be A, but not C. Let me show you. Uh, the measured concentration of A is 0.5 mg per liter, right? But the method detection limit is 1 mg per liter. 1 mg per liter, yeah. So it means our method detection limit is more than whatever concentration we have. It means whenever we are measuring it with the instrument will not give us the correct reading. And correct reading, because why it is not giving us the correct reading? Because method detection limit is more than whatever we have measured concentration. So it is not that our instrument is giving the inaccurate result. No, this is not the mistake of the instrument, but it is just the one uh, what can I say, the one property or one characteristic of instrument we have. Each instrument have different MDL, right? And based on that MDL, we can't say that instrument is giving inaccurate result or accurate result. It is just that whenever we are measuring with any instrument, uh, that will not give us the reliable reading. So if I see the options that we have, it gives not reliable reading. Obviously it will not give, because the detection limit is more than whatever concentration we have. So this one is the right. The compound is definitely absent. No, I'm saying that the concentration is zero point 0.5. How the compound can be definitely absent? This is the wrong statement. The instrument is highly accurate. If we are not able to measure our concentration, how we can say that the instrument is highly accurate or not? Because we are not able to measure it, right? We This is the second step to see that our instrument is accurate or not. But here, before that, the question is either we are able to measure it or not, right? We can't question on the instrument accuracy at this stage, right? In the next stage, I think we can talk about this, but at this stage, when it is just like that, the MDL is 1 mg per liter and our concentration is zero point 0.5, we can't comment on the instrument accuracy as at this time, and that's why this answer is also wrong. The extraction step failed. No, uh, we can't comment on our extraction step, because it may be that our concentration, original concentration, may be zero point 0.5, only 0.5 mg per liter, and whatever we have measured concentration, that is also, like, we can't comment on that extraction step failed or not. So for these two options, sorry, we can't comment. So this is something argument, and based on argument, you are having some inferences, but based on the question that we have, based on the argument we have, we can't make the inference about the accuracy of instrument, and we can't make the inference on the extraction step, whatever the information we have given based on that, right? And that's how a answer is the right one. Is it clear why it is not C but it should be A? Okay. So, if you have any doubt, you can just write. Please don't be afraid, and please don't be think that I'm overpowering. So, whenever you have any doubt, and even if you people are confused, please let me know. Let me know. I will also try to give the better explanation in a better way, right? Okay. So yeah, which of the following are examples of uh, instantaneous measurement? GC analysis, HPLC analysis, conductivity measurement, solvent extraction. I think this is the easiest one, the question that I asked. Yeah, so the answer is C. And why it is instantaneous? Why it is instant? Why, how we can measure it instant? Instant means it is taking no time to measure it, right? GC is taking the time. We have a proper instrument for this, and we have to prepare the sample. Then we should have the carrier gas, then we should have the stationary phase, then um, detector will detect that, and it will give the electrical signal. So that's how it is not instant, right? It is not at the moment it can't give the reading, right? HPLC, this is more sophisticated than GC, so it will take more time, right? Solvent extraction, uh, I get response that we can use conductivity meter giving instant value. Obviously, yeah, you're right. Because we have just 1 meter, we are putting that meter either in the pond or any sample, like wherever we are going, we can carry that meter with us, and then we are just measuring. We are dipping it, and we are having value on the display, and that's how the work is done. So this is instantaneous measurement. So yeah, this is conductivity measurement, and you must already have seen or even measured the conductivity using such kind of meter that I showed you in the slide. Okay, so as I told you, you must have pen and paper. If you have, then it's better. Otherwise, I think the values are very easy to calculate in your mind also. Yeah. So analytical method has an MDL that is equal to 2 mg per liter. The expected concentration of analyte in water is zero point 0.5 mg per liter. What minimum sample volume must be processed? Here we are assuming that we have 100% recovery, so that the analyte mass reach the MDL. And we have four options here: 1 milliliter, 4 milliliter, 4 liter, 0.25 liter. Because the MLD is 2 mg per liter and the concentration is zero point 0.5 mg per liter. So we can't detect it, right? And if we can't detect it, we have to change the volume, right? we have to change the volume so that yeah. And that's how, can you tell me the minimum sample volume that we need? Yeah. So yeah, C is the right answer. That is 4 liter we need. And how 4 liter is needed? You just need to know very simple thing, uh, that we can change the concentration, we can change the volume, but we can't change the mass, right? So, and we already have understood and we learned about the mass conservation, right? So even if you are increasing or decreasing the volume, increasing or decreasing the volume will change the concentration, right? Will change the concentration, but the mass, after increasing or decreasing the volume, the mass will be same, right? So if I know the relation of this mass, volume, and density, what is that relation? Can you just remind it? What is the relation of mass, volume, and concentration? That would be very easy. If this is clear, I think all the question will be very easy for you people. What we know about the mass, volume, and density, or because the density is nothing but concentration. We already have learned that our concentration or density is equal to mass by volume, right? And mass is equal to concentration, or you can say density multiplied by volume. So what I'm saying is that the mass will be same, right? Mass before and after will be same. Even if I'm changing the concentration or if I'm changing the volume, the mass will be same, right? So just see here, this one, if we have 2 mg per liter and if this is the concentration, right? Okay, so this is the one concentration. The second thing is the expected concentration of analyte in water is 0.5 mg per liter. Volume is equal to mass by concentration. Yeah, you're right. You can, yes, you can just shift it from left to right, right? So what we are learning from here, that the expected concentration of analyte in water is 0.5 mg per liter. So it means in 1 liter the mass is 0.5 mg, right? So what I can say is that uh, here, because this is concentration multiplied by volume, so here we have zero point 0.5 and 1, because it is in 1 liter. The concentration here will be 2 and we just need the volume. So I think this is how also you can calculate one way. But yeah, so this will be 2 divided by zero point 0.5 is equal to 4. And I think the next one, I think this will help you more. That, sorry, that mass is equal to concentration multiplied by volume. And oh, sorry, you gave me wrong one, or let me see. Yeah, same. So because our concentration is zero point 0.5 mg per liter, we need the volume. So I just flipped in a different way. I think that that's how my equation got wrong that side. But the thing is, we just know the concentration, and that concentration is zero point 0.5. We just need the volume, right? And because we know here it is 2 mg, and this 2 mg came from nothing but 2 mg per liter multiplied by 1 liter, right? And that's how. And because c is already known, that is zero point 0.5, and v you need to know, and that's how this will be the 4 liter. So we need 4 liter of volume if we want to able to detect 2.5 mg per liter in the instrument. Okay, so the next question is, instrument linear range is 10 to 40 mg per liter. Sample concentration is 100 mg per liter. What is the minimum dilution factor? Please make it understand that I want the dilution factor required to bring the sample concentration within the linear range. And I have four options here: 2, 2.5, 4, and 10. I just need the dilution factor. I don't need volume. I don't need concentration, but I need the dilution factor. Dilution factor will be what? Um, D. I don't think that D is the right answer. Because just see, you just need to understand. This is, let's say, our um, calibration curve, right? And your value is somewhere here, and your linear range is 10 to 40, right? And this is 100, let's say. So you just need to cross this one only. We are not worrying about this 10, right? If the instrument linear range is 10 to 40, and our sample concentration is more than this range, then we just need to cross this 40, because we need the value between 10 to 40. So we are not concerning much about 10 mg per liter, but our concern will be just cross that 40 mg per liter. So it will be what? In two way, I think you can calculate. So the one is, dilution factor is nothing but this is the ratio, right? Ratio either of concentration or ratio either of volume. So either you can calculate the volume, or you just know the concentration, right? You know the concentration of instrument, you know the concentration of sample. You just need to divide, because the dilution factor is nothing but this is the ratio of either the concentration or the volume, right? Okay, so let me tell you, the answer is 2.5. And how it will be the 2.5? This is easily 100 upon 40. So the dilution factor will be 2.5. Let me also show you in the next slide. Yeah. So we need the concentration between 10 to 40, right? And our sample is too concentrated because we have more analyte, that is 100 mg per liter. So we need to dilute it, right? We need to dilute it. And we, as I told you, mass will be equal. If after dilution, before dilution. And that's why we are hearing this is nothing but mass, this is nothing but mass, mass before dilution, mass after dilution, right? And mass will be same, because we already have learned about the conservation of mass. Wherever our pollutant, wherever our analyte will go, the mass will be same. We are just increasing or decreasing. So if we are gonna dilute it, if we're gonna dilute it, so the dilution factor will be C1 upon C2, right? And we know that C1 is equal to 100 mg per liter. C2, we just need to cross that, right? So this is to ensure the dilution concentration is at most 40 mg per liter, right? We do not need more concentration than that. We need less concentration. That's why 40 is important compared to the 10 mg per liter. And that's how the answer will be 2.5. Okay. Let's say the initial concentration of your analyte is zero point 0.5 mg per liter. I have wrongly taken 10 pp. Yeah, sometime it happened actually. So don't worry. We just have to see whether our concentration is more than our linear range or less than our linear range. Based on that, we have to decide whether we are taking the starting point or we are taking the end point of our linear range, right? Okay, so the next question is initial concentration of analyte is zero point 0.5 mg per liter, and here MDL it means our concentration is less as comparison to the detection limit. If 500 milliliter of sample is evaporated to 50 milliliter, what is the final concentration? If initial concentration was zero point 0.5 mg per liter, but the volume of our sample was 500 milliliter, right? But because what we need is we need the concentration 2 mg per liter, and with that concentration we need the volume 50 mg per liter. So I just need to know the final concentration. So here again, this will be C1 V1 is equal to C. We need to change the initial concentration, right? Or because based on like whatever our MDL we have, based on that we have to change the concentration. We already have reduced the sample volume from 500 ml to 50 ml. What we need to first calculate is MDL important for us right now? Because if you just see the trickiness of the question is not asking you the range to be within MDL or above the MDL. The question is not asking about that thing, right? So this MDL is just to confuse you. because like the question is not want from you that our concentration will be should be more than mdl. This is here just to confuse you. So now you can apply that C1V1 is equal to C2V2. Because the question is not asking you whether your concentration should be above that MDL. So that's why the value of MDL may be useless for you. Given no loss of analyte, let me see the answer that you gave. This is zero point 0.5 mg per liter. Uh, Not exactly. The thing is, just keep in mind that your mass will be same, right? So the thing is, initially you had the concentration zero point 0.5 mg per liter, right? So this is your C1, and your V1 was, your volume was what? This was 100 milliliter, right? And because you know the mass before changing the volume and after changing the volume will be same, you just need to calculate C2, and V2 is given as 50 milliliter, right? So if you are cancelling it, 1, 10, can you calculate now C2? What will be the C2? C2 will be 5, is it? Or something else? Yeah. So it will be 5, right? So you here the question was just MDL was just to confuse you, because it was not asking you that you just dilute it so that it should be above that MDL. It was just to make you confused, right? And we know that the mass conservation, the mass before dilution and after dilution will be the same, and we know that mass will be equal to concentration upon volume. Initially, the concentration was zero point 0.5, the volume was 500 ml, right? And the final volume we need 50 milliliter. So the concentration will obviously be changed, right? And what it will be, this will, we can calculate using C1V1 is equal to C2V2, and that's how this will be the 5 mg per liter. Okay. The next question is, uh, again, same type of question. 1 milliliter of 100 mg per liter solution is diluted to total volume 4 ml. What will be the final concentration? And we have four options here: 100 mg per liter, 75 mg per liter, 25 mg per liter, and 400 mg per liter. Again, the same type. The mass will be same, right? If the mass will be same, then, and mass, we know that this is the concentration multiplied by volume. So mass before dilution, after dilution will be same. You just need to equate that two condition, before dilution and after dilution. So this will be something like 1 multiplied by 100 is equal to 4 multiplied by some concentration. So I got response C, and yeah, the answer is C. So because this is nothing but 100 multiply 100 divided by 4, and that will give us 25. So I don't think that you need the explanation for this because this is simple one. Okay. Again, the instrument MDL is 2 mg per liter, measured concentration after dilution. We already have diluted, and after dilution, the concentration is 1.5 mg per liter, which is true. Result is accurate and valid. Sample must be further diluted. Result is unreliable. Increased calibration point. Little tricky, but I think you can answer. I think you are confused among option B and C, right? Okay, so I got a new answer that is A. Result is accurate and valid. We are not able to measuring it, right? We are not able to measuring it because the MDL is 2 mg per liter. We will not able to measure it. Somehow it is written that this is the measured concentration after dilution is 1.5, but how we can able to make the measurement if the MDL is 2 mg per liter? It will not give, even if we are measuring this 1.5 mg per liter in that instrument where the MDL is 2 mg per liter, um it will give you the 2 mg per liter. It means it is not giving us the accurate result and it is not valid because the instrument will give you the 2 mg per liter only because the MDL is 2 mg per liter. And because we already have diluted it, so the dilution again is not a right choice. So the result is unreliable actually here. And increase calibration point, even after increasing the calibration nothing will happen because increasing the calibration point can give you more accuracy, but if MDL is 2 mg per liter, even after having more calibration point, you can't increase the sensitivity, right? So that's how the very simple thing is because MDL is 2 mg per liter, you can't measure 1.5 mg per liter, and that's how the result is accurate and valid. This is out of scope actually because we can measure it. So how we can comment on the result part, right? And we already have done the dilution. Then B is not uh, should not be the first or the foremost answer. So the answer will be the result is unreliable, right? So the C answer is the right one. This you already know that is should be more than 3, and this here it is standard deviation, 3 standard deviation. Okay, so now we are moving to the extraction part, right? So as we already know that for example if we have arsenic or nickel in the water, right? And these are inorganic and these are present in very small amount. So and we need to measure it in the instrument. So to make it measured, we need to change the solvent, right? So the question here is, in liquid extraction, the best solvent for extracting organic compound A from water should be completely miscible with water, have low affinity with A, have a high partition coefficient, have high polarity similar to water. Okay, so yeah, I got right answer. that is C. So it is something that you have organic compound A in the water, and because for the instrument to measure it, first thing is that uh, it is we the solvent should be different from the water, so we need to change the solvent, the first thing. The second thing is we need to concentrate this A, right? And to make it so first we have to remove this A from the water, or you can say that we have to move this A into different solvent. And this solvent affinity, or to bind or to make the bond with this solvent. So let's say this water is solvent A dash, and this is B dash. So to make it soluble in the B dash, what is the requirement? That its solubility will be should be more in B dash as comparison to the A dash, right? So this is nothing but, again, we are talking about the partitioning coefficient, how the affinity of A to move to A dash or to the B dash. And the affinity should be more for the B dash to remove it from the water and to make it soluble in B dash, right? And that's why this should have more partitioning coefficient. So that's how C answer is the right one. You already know about this whenever we are talking about the partition coefficient, right? So the partition coefficient of any organic phase uh, as comparison to the water phase, so this will be the ratio. So pollutant A in the water and pollutant A in the organic phase, right? So the partition coefficient will be the concentration of A in organic phase divided by the concentration of A in water phase. And the ratio, if ratio is 100 or if ratio is more, so it means that the concentration of concentration of A in organic phase is more. It means it is moving toward organic phase, right? And that's how the answer will be according to this concept only. Okay, if 1 liter of water is extracted into 20 ml of organic solvent, the theoretical concentration factor is, if the concentrate if the mass of so let's say if we have A, and if that A was present in 1 liter of water, but now we are moving this A, the mass of A, into 20 ml of organic solvent, so the theoretical concentration factor will be what? Yeah, so this will be, yeah, D is the right answer. That this will be 50 times, right? And how this will be 50 times? Because 1 liter equal to, yeah, 1000 milliliter divide by 20, because this is we need the ratio, right? We need the ratio of volume. So 1 liter divide by 20 milliliter, and that will give you the 50 time. So what we are doing, the we are concentrating it, we are concentrating our pollutant A 50 time to make it 20 ml, to make it into 20 ml, right? So 50 is the right answer. If compound A has, this is partition coefficient and this star is equilibrium, and partition coefficient of the solvent versus water, and this is 100, most of A will be found in water phase, solvent phase, equal distribution, and air phase? I think this is right, and this is very easy question. So we have partition coefficient. This is 100, and if we have partition coefficient 100, then where this A will go? To the water phase, to the solvent phase, to have the equal distribution among solvent and water, or to be in air phase? We already have learned that this Ka, and this is equilibrium, and because this is solvent water, right? So this is concentration of A, concentration of A in solvent divide by concentration of A in water, right? And if this is equal to 100, it means the concentration of A in solvent is 100 times more than the concentration of A in water. It means your A will go more in the solvent as comparison to the water, or there is a no any equal distribution because it has more affinity toward the solvent. And that's how we are selecting the solvent in such a way that affinity or the partition coefficient of that solvent should be very high to extract that from water, right? uh, yeah, you gave me answer B, and yeah, so this will be in solvent phase, so B is the right answer. Okay, after extraction, why is solvent evaporation used? To decrease detection limit, to reduce solvent polarity, to further concentrate the analyte, to reduce partition coefficient. First, what we learned about the solvent. So if we have A in water, so this is, let's say, water, the first thing is we need to remove that A, and we need that A in some solvent, right? So first, what we learned about that solvent is that the partition coefficient of this solvent should be higher as comparison to the water. Second property is that solvent should be, yeah, volatile in nature. It should be volatile in nature. How the volatility of that solvent will help us? Because with the time the solvent will evaporate, and that's how the concentration of A will increase. And for the instrument to measure uh, the concentration of A, we need high concentration of A in any solvent. So if we have solvent that have more volatility, that can volatile, that can evaporate, um, that's how this will concentrate the analyte. So we have talked about the two property of the solvent. The first thing is partition coefficient should be higher, and second, it should be volatile. And what is the use of volatile? Because it will concentrate the analyte. What is the use of higher partition coefficient? More of the uh, component or pollutant A will go to the solvent as comparison to be in water. That's how these two properties very important to make any solvent for a particular pollutant to be measured in particular instrument. Yeah, so that's how C is the right answer. Okay. Uh, If we okay, here what I did is, uh, a lot of information is already given. So if 1 liter water contain 0.2 mg per liter of A, so here the total mass of A will be concentration by volume, and this will be zero point 0.2 mg, right? If fully transferred to 10 milliliter solvent, the new concentration, so the new concentration will be, because here what we are doing is, um, um, if we are transferring it to 10 milliliter, then the concentration will be changed, and here the concentration will be 20 mg per liter. So what is the concentration factor? 10x, 20x, 50x, or 100x? Again, we are talking about the factor, and factor is the ratio of the same unit, either it is concentration or it is the volume. So factor is, most of the time, these are uh, the ratio of the same unit or same parameter. So what is the concentration factor? So yeah, D is the right answer. And why D is the right answer? Because what we are doing is, new concentration we have 20 mg per liter, and initial concentration was zero point 0.2, and when we are dividing it, this is giving us the 100 times, right? So we are making it 100 time more concentration as comparison to the original one, right? And that's how this will be the 100 times. So D answer is the right one. So very simple. 20 divided by zero point 0.2, and that's how this will be the 100. Or you can also, as I told you, if we have some factor or dilution factor or this one, so we can just divide either either the concentration or volume, and based on volume also you can calculate the same thing. Volume 1000 milliliter divided by 10 milliliter, and this is how this will again give you 100 concentration factor. Okay, so we talked about liquid extraction, right? And this question is about the solid phase extraction. Analyte A is first retained by uh, dissolution, adsorption onto solvent, evaporation, centrifugation. So this is something that we have pollutant A, and that pollutant A is in water, right? But to measure it in the instrument, we need that concentration A in some solvent. But first, what we need to do is we need to remove this A from water, and we can take the help of some solid phase. So, for example, can you give me one example of solid phase that we can use? Can you give me one example how we can what solid we can use to extract any pollutant A? A very famous charcoal. Let's say we have activated charcoal, right? Yeah. So let's say we have activated charcoal, then we can, what we can do is we can remove this water, or this water will be removed when this A will be attached with the activated charcoal. So, but how it will be attached to activated charcoal? Then, yeah, you gave me right answer, that there will be firstly adsorption onto the sorbent. This is the first step how we can move our pollutant A into onto solid. So, yeah, B is the right answer. These are the steps that we have to follow if we are using the solid phase to remove water from that solvent, from that pollutant A. So let's say this is our activated charcoal. Let's say this is activated charcoal. Then we add our sample. Let's say this sample is A. So we are adding this sample A here, and then what will happen? Um uh, Here the analyte is this red color, and these are some interference, right? So the first thing is, this solid should be in such a way that it can absorb uh, a sample as much as possible. Then so there will be our sample on this solid phase. The next step will be to remove that sample from the solid. But yeah, there are some processes that we can follow. For example, washing. This washing will remove some interference, and after that we have the last step, that is the elution. And in that elution, what will happen? There is a detachment of your A from your solid, and that's how this will be extracted, right? And this is better than liquid extraction. Okay. And yeah, very simple one is that there will be adsorption, but we can also utilize the ion exchange. You people already know about some resin that we can use to absorb some kind of ions and cations, and that's how we have different adsorbent and a different solid phase by which we can extract that, right? Okay. So based on that figure only that I showed you, what is the purpose of elution step in SPE? Remove water, decrease detection limit, dissolve analyte from solvent, reduce solvent polarity. Yeah. So yeah, Lakshmi, C is the right answer, and we already have talked about this, right? Here, not here, but here we already have talked about this. First we have conditioning, then sample addition, then washing, and then elution. And in this, in that eluting, you can see that our sample will be detached from that solid, right? So that's what I asked in the question. So this will be, it will dissolve analyte from sorbent, and that's how the C answer is the right one. Okay, so if we are comparing the liquid extraction and solid phase extraction, so compared to LLE, SPE generally use a large solvent volume, no sorbent phase, smaller volume, better selectivity, only volatile analytes. So now we are comparing the liquid extraction to the solid phase extraction, and you need to tell me which one is the right and which one is wrong. Yeah, so Chechi gave me C answer, that is the smaller volume and better selectivity. Yeah, as I told you, uh, uh, SPE is better than LEE, because the first thing is we can concentrate more. So for example, um, we have that A in water, right? And here, if we are using some solvent, and here we are using some solid. So after solid, we will have just mostly A in very small solvent. But here, because we are using a lot of solvent, so in liquid extraction, we will have but in different solvent, right? And that solvent volume will be more as comparison to the solid solvent after whatever we are using to eluting it, right? So SPE have smaller volume because the volume after liquid extraction is more. Better selectivity. We have a lot different type of sorbent we can use. As I told you, we can use adsorbent, right? We can use some adsorbent. We can use some resins, and that resins are very particular to some kind of cations and anions. So the selectivity is more in solid phase extraction as comparison to the liquid phase extraction. That's why C is the right answer. Okay. If instrument read 1 mg per liter for the extract, what is the mass of A present in 1 milliliter of extract? Here the concentration is 1 mg per liter. And what will be the mass of A that will present in 1 milliliter of extract? Very simple. But because I asked you in different, not different unit, but like this is micro, so you should give me the answer. I think you just need to see. Here we have liter, here we have milliliter, and here we have mg. So based on that, I think you will be little confused. So please be aware of this while doing the calculation. I want the mass, right? And for mass, I already have told you. Uh, if we are changing the volume, right? Then we just need have like before changing the volume and after the volume changing, the mass will be same. Then the C1 V1 is equal to C2 V2. JG gave me answer A, 1 microgram. Yeah, Lakshmi also gave me. So I think now you understood what I wanted to say. Please be aware about this. So this is something here, if instrument is reading 1 mg per liter. So here we are having the concentration is 1 mg per liter, right? So it means here the volume is 1000 milliliter, right? Because here we have the milliliter, and we need the concentration multiply by the concentration when the volume is 1 ml, right? And that's how you can calculate this, right? And because we already have this one, did I give you the wrong statement? If the volume, it is a wrong or what? We should have why we are talking about such kind of things. I think I have explanation here if I'm wrong here. Yeah. So this is something we know that mass is equal to concentration upon volume, right? And our mass is equal to concentration is 1 mg per liter, and we need the volume, and that volume is 0.001 liter, right? uh, yeah. So here if it is a liter, then we also have here it should be in liter, or if we are making it change to milliliter, then here it should be milliliter. And that's how we already have 10 raised to power minus 3. Here we also have 10 raised to power minus 3. So this 10 raised to power minus 3, 10 raised to power minus 3 will give you the 10 raised to power minus 6, and this is how this will be the microgram. Okay, now we are talking about the recovery. As I told you, whenever we are using the liquid liquid extraction or solid phase extraction, it is near to impossible that after extraction, whatever the mass we had initially, it will be the same mass. Okay, so let's say um, we have here let's say we have the concentration that is 2 mg per liter in the water, but after extracting it into some solvent, the concentration may be, let's say, 1.8 mg per liter. So what does it mean then? The recovery is not 100%. Recovery is not 100%. Recovery has been reduced. So there is a term that recovery is very important, and that's why we need to select the solvent where the recovery is near to, there should be the recovery near to 100%, right? But this is impossible to have the recovery of 100%. So this question is based on that only. A 1 liter water sample is extracted into 25 milliliter organic solvent, and the measured concentration in the extract is 2 mg per liter. We are assuming here 100% recovery. What was the original concentration in water? So this is very simple because right now we are just assuming recovery 100% only. So this will be the same question like what we already have solved, because here the recovery is 100%. We just need not to divide or multiply with some recovery factor. So we are changing the volume from 1 liter, that is 1000 milliliter, to 25 milliliter. So we are reducing the volume, and if we are reducing the volume, we are expecting that concentration should be increased from and so if we are extracting it to 25 milliliter, then the measured concentration in the extract is 2 mg per liter. So for 25 milliliter, the concentration is 2 mg per liter. And when the pollutant A was in water, where the volume was 1 liter, what was that original concentration in water? So this is just C1V1 is equal to C2V2. I think very simple. Is it? One thousand multiplied by concentration is equal to 25 multiplied by 2. And you just need to calculate the concentration, C1. So will it be like 50 divided by 1000? Yeah. Something 50 divided by 1000. So what will be? It is B. You just need to change that. You just be aware about the unit. What I'm saying is 1000 milliliter, that is 1 liter, right? So 1 liter of the sample will have some concentration that we need to calculate, is equal to, we have 2 mg of the concentration in 25 ml of water, ml of organic solvent. So this is something, this is 50, right? This is 50. So what it will be? 50 divided by 1000. So what it will be? 0. 0.05 mg per liter. Very simple. But the next question is where we have 80% recovery. I think this we already have calculated. Yeah, The same question, the same values we have, but here we are assuming 80% recovery. What was the original concentration in water? You just need to know that if it is a 80% recovery means 80% of original concentration. No, A is not the right answer. Just see that 80% of original concentration will be equal to something like this. The measured concentration is 2 mg per liter, right? We have measured it and we found that this is 2 mg per liter, but but we have 80% recovery. It means our original concentration should be more. Is it? What you will do? Let me show you. Very simple. What I told you that we already have we already have calculated this in the last question, right? This was 0.05 mg, but because we know that this one represent just the 80% of the original mass, right? And if it is just the original, then if we are calculating the true one, because we know that as I told you, 80% of true one is the measured one, right? Is the measured one. So if we are calculating this true one, we just need to divide it with 0.8. Is it? Yeah, this one. And we already have calculated this 0.05, that was the measured one, and we need to divide it with the uh, divide it with the recovery factor, right? This is 0.5 0.8, because 80% is only recovered, 80% of the true value, and we need to calculate the true value, and we already have the measured value, that is 0.05, and that's how this will be 0.05 divided by 0.8, and this will give you 0.0625 mg. And whenever we are calculating it in the concentration, then this is 0.0625 mg per liter. And please be aware that we need here the mass, right? Okay. Again, we have one question on recovery also. We have 500 milliliter water sample. We are extracting into 10 milliliter solvent. Okay. Uh, our solvent first was in water, and then we are moving that pollutant A in solvent. Initially, the volume was 500 milliliter, and then solvent volume is 10 milliliter. Extraction concentration measured is 5 mg per liter. So when we measured with the instrument, we found that the concentration is 5 mg per liter. And because recovery was 80%, what is the original water concentration? It should be more, right? It should be more, because if the recovery would be 100%, then the extracted concentration that we measured will be equal to the true concentration. But because the recovery is just the 80%, it means our original concentration should be higher than this 5 mg per liter. But how much? And please don't be confused, uh, because I'm telling you that it should be it should be more than 5 mg per liter, because here we already have extracted from 500 milliliter to 10 ml, so we already have concentrated it, right? So, and if we are talking about the water, then the concentration will be yeah, low. um, I'm thinking that you are not getting confused, right? Because we have extracted it to 10 milliliter solvent, then this is 5 mg per liter. But whenever we are seeing the concentration in 500 ml, because we need to find out the concentration is 500 ml, then this will be lower because it is not 10 ml, this is 500 ml. Okay, so Lakshmi gave me answer C. Yeah, and the answer is only C. So how you calculate it is, first you will calculate the mass, right? Mass of the measured one. So this was your concentration, and this 0.1, what it is, this is your volume, right? So first what you are doing is you are calculating the mass. The mass of the measured one is 0.05, but you know that mass will be higher initially because the recovery is just the 80%. So the point that you need to understand that whenever we are calculating before and after recovering, we have to deal with the mass, right? The mass after recovery and mass before recovery. We are not talking about here about concentration initially, right? So first what we did is we calculated the mass before recovery. uh, Mass before recovery will be higher because the 80% of this will be only 0.05. If we have the mass, then we can calculate the concentration. If this is the mass, and we know that we have um, 500 milliliter volume, right? And this will be 0.5. So this is how we can calculate the concentration of our pollutant A before recovery. So this will be 0.125 mg per liter. If there is any doubts, please let me know. Otherwise, we can move to the next question. Okay, which process most commonly cause loss of volatile organic compound during sample handling? Filtration, volatilization, precipitation, sedimentation. Yeah, I think the question itself is giving the answer. Yeah, so you people gave me right answer. That is B. Because it is volatile in nature, then obviously we can expect that the sum of the pollutant A will go to the air because this is volatile. This will evaporate and this will go to the air. And this is how we can lose some of our concentration, some of our mass. Organic pollutant should preferably be stored in plastic container, glass container, open metal container, paper containers. Right now, what we are focusing on, uh, b- uh, because we have a lot of steps, right? We have row one, and then if we need to analyze it into the instrument, we have a lot of steps, right? And in each step there will be some loss of our A, right? And if we don't want to lose it, we need to take care of a lot of things. And the one thing is in which container we are putting that pollutant. So if it is the organic pollutant, where we will put it? In plastic container or glass container or open metal container or paper container? Lakshmi already given me a B answer. Yeah. So B, what is the right one? Why in glass? Why in the glass container if we have the organic pollutant? The purpose of putting that organic pollutant in the glass container is so that there is no any kind of reactivity. Plastic, uh, yeah, corrosion and reactivity. So in the plastic, there will not be corrosion, but there will be the reactivity. But why the reactivity with the plastic? Because plastic is also made up of a lot of monomer of the carbon only, right? Or the polymer of carbon, monomer to polymer. And yeah, so plastic is made up of the carbon polymers, and carbon polymers are nothing but this is also the organic thing. Organic will like organic, and uh, there will be more affinity to it. So plastic, whenever we will extract our organic pollutant to somewhere else, then plastic, there will always be some pollutant attached to this plastic because it is loving that plastic, right? Open metal, as you said, corrosivity and the reactivity. Paper container, this is again, paper is also cellulose thing, right? This is also the carbon thing, so carbon will love the carbon, and that's how B is the right answer. If we have inorganic metal ions, it should be preferably be stored in plastic container, glass container, paper bottle, untreated metal container. Right now we do not have organic, but we have inorganic metal ions. So where you will store that? Into what? So we will store it in plastic container. Because why? Because the plastic is organic and there will be no reaction between inorganic and organic, so it is better to put that into the plastic container, and that's how A answer will be the right one. Water sample for heavy metal analysis are typically acidified with nitric acid. Why? So I have four options: increase volatilization, prevent biodegradation and precipitation, increase adsorption on container walls, remove dissolved oxygen. Um, uh, Not to remove dissolved oxygen because nitric acid already have oxygen. Then we can't comment on to remove the dissolved oxygen because it is HNO3, right? We already have oxygen in it. Yeah, B answer is actually, yeah, B answer is the right one. That we need to prevent the biodegradation and precipitation. If you will go to the reaction, then what you will get to know that if we are doing the acidification, if we will do the acidification of any metal, and so this will, what will happen? So whenever we have heavy metal, and if we have some acid, that is the nitric acid, that will prevent such kind of reaction, right? It will prevent the metal precipitation, it will inhibit the microbial activity, and it will keep metal in dissolved form. That's why it is better if we have heavy metal, then we can put it into the nitric acid. Loss of organic analyte due to adsorption is most likely when samples are stored in clean glass bottle, sample are filtered immediately, sample are stored in plastic, samples are acidified properly. We already have discussed about such kind of question when we were talking about in which container we should put that organic analyte and why. Yeah. um Not D. The answer will be C only, because we already have talked about this, right? uh, Organic will like the organic, and if we are storing that into the plastic, it means there will be some adsorption. And whenever we are moving our organic analyte to somewhere else, there will always be some adsorption to the plastic, right? So that's how there will be always be some loss of the analyte. Um and that's how we need to calculate again the recovery percentage. So note, samples are acidified properly. uh, this is You can say that yeah, we have a lot of reason for the loss of the organic analyte. This may be the biodegradation, right? This may be the reactivity, and a lot, right? But the question here is due to adsorption. If I didn't write due to adsorption, then D also may be the right answer, because maybe because of the biodegradation or the reactivity, there may be the loss of the organic analyte, right? But here the question is due to adsorption. For that adsorption, C must be the right answer. Is it clear? It is not D, but it should be C. Okay, so the next question is, why should hat space be avoided when collected sample from for volatile organic compound? It increases adsorption onto containers walls. It allow analyte to Ka star 21. It increase biodegradation. It reduce Henry constant. So you people already know about this headspace, right? So if this is the container and this is our cork, and if we are putting water, and water have A, but this space is empty, we do not, so this is headspace. So whenever we are collecting the sample, mostly VOCs, then we should avoid headspace. But why? Because not A. Whenever you are talking about the VOCs, they can volatile and they can go to the air, right? And if it is going to the air, and we already have here water, air, uh, it will reduce Henry constant. No, you are the Henry constant is opposite. No doubt it is related to the Henry constant, but inverse to the Henry constant. So this will be the this one, Ka21. So just keep in mind that if we have VOCs will go from water to air, right? Will go water to air, because in the head space we have air, so our pollutant will go to the air. And that's how the thing is, we need to talk about the partition coefficient Ka. And Ka, water and air, we have to talk about 2 1 or 1 2, right? But the Henry constant, it is inverse to the Henry constant. So B answer is the right one because this is giving you the generalized one. So B answer is the right one. Okay. For organic chemical analysis, the bottle cap liner should ideally be bare metal, untreated plastic, inert material, rubber. I think this is the simple question that I put. Maybe you can answer is quickly. Bottle cap liner, you already know about this. So let's say if this is the bottle and this is our to close it, right? And to close it tight, we should have the cap liner. Rubber is again a polymer. Rubber is again a polymer, and if we are putting a rubber cap liner and we have organic, then there may be some reaction or adsorption. Yeah, so C is the right answer actually. Yeah, there should be inert material. Rubber is the polymer, and if you people know that, yeah, in the South India we do have rubber plants, and yeah, if you go to the structural formula of the rubber, this is organic. Adsorption losses are most likely when samples are stored in clean glass bottle, dust presence inside container, sample are kept at low temperature, no headspace is present. I think this is again very simple question. Yeah, so there will be some adsorption losses when we will have some dust in the container, because around the dust, some pollutant A may be adsorbed, right? So that's how B answer is the right one. Which combination minimize loss of volatile analytes? Large headspace, warm storage, no headspace, low temperature, plastic container, open cap, high temperature, shaking. Which will minimize the loss of volatile analytes? No, we need to minimize the loss, right? Yeah, and B is the right answer, not A. If we are lowering the temperature, if we do have, yeah, it's okay. If we have low temperature and if we have no headspace, then yeah, we can minimize the loss of volatile analytes. Okay, I think yeah. So now we are moving to so whenever as I told you, we have 80% recovery or 70% recovery, right? Something like that. To calculate this recovery, we have different methods, and we have three type of methods actually. Right now what we will discuss, the first is laboratory control sample method, the second is metric spike, the third is surrogate standard, and you need to tell me the difference between these three methods. So LCS evaluate method accuracy in the clean metrics, MS evaluate metrics effect in the real sample, SS monitor recovering in each individual sample. LCS evaluate matrix effect, MS evaluate instrument drift, and SS replace calibration. LCS correct recovery in real sample, MS replace surrogate standard, and SS evaluate detection limit. All three methods have the same purpose. I will tell you, don't worry about this. If you don't know about these three methods, then I will let you know. Don't worry about this. So to calculate this recovery, right, it is important to calculate the recovery. We have three type of methods that we can follow. And these three are LCS, MS, and SS. And you should know the difference between these three.
Lakshmi gave me answer A, and yeah, the answer A is the right one. So let me tell you how we can calculate this recovery. I think next slide okay. So it is very simple. If we are talking about the laboratory control sample, so first we have real water. So this is a real water having the A, right? And we will calculate the concentration here after like the concentration of A, and here we have the real water. But we can also do, what we can do is, we can put the known concentration of A in distilled water or some clean water, and then uh, after undergoing into the multiple step, we can calculate the concentration using the instrument of this A, right? And most of the time, whatever we have known concentration, it may be 5 mg per liter, right? And here it may be 4 mg per liter. It means we have we have 80% recovery rate, right? 20% is lost in multiple step. But the disadvantage of this is that this is the real water. Real water will have different characteristic, right? And here we are using the clean water, so this is not the real situation. We are calculating the recovery, but not in the real situation. So this is the limitation of laboratory control sample, right? So that's why so these have the limitations. So that's why we go to the metric spike. In the metric spike, what we do is, first we have we what we are doing is, we have water, and in water we have A, and we will analyze it and we will calculate the concentration of A. Then the second, what we are doing, we have water. In water we have A, but we are also adding some known amount of A, and then we will again calculate some concentration of A, and based on that we can tell what is the recovery rate. Okay, so this will be come under the metric spice uh, metric spike. Surrogate means, here what you are uh, using is, you are using the proxy of A, so some radioactive. So for example, your analyte have something. So you, if you need to measure, let's say, some analyte H2S, if you need to measure the analyte H2S, then what you can do is, you can just use here deuterium, right? And you can put some standard that have a different radioactive, and then you can see the recovery, and that's how it will give you the exact recovery rate. But this is very expensive case. Surrogate standard is very expensive, that's why mostly we are relying on the metric spike, and A is giving you the better um, explanation about these three methods. Why does a laboratory control sample not account for metric effect? Metric effect means the solvent effect. It contain no analyte. It use pure solvent instead of real sample metric. It is analyzed by a different instrument. It correct for recovery automatically. Yeah, so Lakshmi gave me B, and I already have told you, in laboratory control sample, we are adding some standard. We are adding the known concentration in some clean water. But in real, we do not have that clean water. If we are going to collect that sample from the river or from like any pond, the water quality will be very different from that clean one, right? And that's how the recovery rate in this sample will be very different from this one. So it means, whenever we have laboratory control sample, we are not accounting the water characteristic, yeah. And this is nothing but the metric effect, and that's why B answer is the right one. I think one, two question we will solve, and then yeah. Uh, then we have surrogate standard, and in surrogate standard, let's say we are using deuterated naphthalene D8 is added to every real sample before extraction. 2. Increase instrument sensitivity, replace external calibration, monitor recovery and metric loss in each sample, change Henry constant. I already have talked about this surrogate standard, what it is. So, what is the need of this surrogate standard? Yeah, C is the right answer because we are monitoring the recovery, and second, because we are putting that radioactive version of our pollutant A in the real water only, and that's why it is also calculating the loss in the metric, like in the real water. So that's why C is the right answer. Time is up, and I have some question. I think this question we can solve in next week. So I think I should stop here because the time is up. So yeah, we have few questions that we can solve related. So what we need to cover in the next week is a few question about this standard, and we didn't touch yet the blank. We will talk about the blank also in the next week, what different type of blank we have and what is the purpose of such kind of blanks. So this is the portion that we are yet to cover, that we will cover in next week. So thank you so much, and we will meet next week Tuesday 6 to 8 p.m. only. Thank you so much for showing the patience and to participate actively. Thank you so much. I think you can go, and yeah, you can leave the call.